Hello. Today we're going to talk about Gauss Law. So this law, it's very strongly related to the Coulomb's law, and that can be shown later. We're not gonna show the relationship, but just a note. Okay, so first we're going to define the electric flux. So before we do that, we want to talk about the direction of an area. So we treat area as a vector, right? So let's say if we have an area here that we care about in space, like that, okay? And then the normal vector is considered the area's vector. So that's, 90 degrees to this plane here, right? And then if you have the electric field, so let's say electric field is going this way. So we would define electric field somewhere else, but this is called electric field. Okay. And electric field is defined as F is equal to E, so both are vector, and then times Q. Okay. So basically it's a force per charge. Okay. So that's a force per charge concept. So it's kind of like a force, but divided by charge. Anyway, you have an electric field going this way. So now electric flux is defined as the E has a projection that's going this way. Let's call this one theta here. So this will be E cosine theta. Right. So you can also call this one to be the E perpendicular, right? Perpendicular to the area. So electric flux is defined as, I'm going to call that phi, okay? So phi is defined as, and E is just for electric. It's defined as E vector cosine theta times the A. Okay, so basically it's the electric field that's parallel to the area's vector, right? So basically this is the amount that you have this one here parallel to the A vector, right? And you times them together. So electric field that's parallel to the A vector, but it's perpendicular to the surface of the area, right? Okay, so this is also called E perpendicular A. Okay, yeah. So that's the notation, E perpendicular, right? Or is it EA cosine theta? So it's a little bit like the work, right? So F times D times cosine theta. So this is so-called inner product, right? This kind of definition is called inner product. All right. Okay, so now we're going to talk about the electric flux over a closed surface, right? So this is only an area, but now we're going to talk about like a closed surface. All right, so let's talk about that. Okay, so let's say you have a closed surface, right? It may not be a sphere, but it's just, it's a closed surface. So this is like a surface here for, in the space, right? So let's say you have a flux that's coming out from this area here, and let's look at it as a little a right there. So we're going to call this one here. Check what the book says, right? So we're going to call that one, say, delta A1, right? And we're going to call this one E1, okay? E1. And then this delta A1 has a vector that's going this way, right? This is also called delta A1 vector, okay? And then you have this one here, you're going to call that theta 1, right? I'm going to call that theta 1, all right? So then the electric flux through this delta A1, right? So V A1, right? It's equal to E1 cosine theta 1, right? Times the delta A1, okay? So this is your E1 perpendicular times the delta A1, okay? So same idea. Now, if you do that for all the area, all the little area that's around this surface, right? And you're going to sum them together. So you're going to sum them together. You're going to call that a total electric flux, right? Total electric flux, right? Over this surface, right? This surface, right? The entire surface, right? So like here would be another, so delta A2, right? Okay. And it'll be delta A3, and you add them all together, right? So now once you do that, it's going to become a summation of E, I, right? And then perpendicular delta A, I, right? So I equal to 1 to some kind of n, right? So it depends on how you break this surface into how many pieces, okay? So this is called the electric flux, all right? So, so if you add this all together, you can also give a notation. Instead of writing the EI, you can just say, you know, if you simplify a little bit, you still break it into EI, but you can say, like a, you know, perpendicular times this delta A, right? So this one here associated with the delta A, but still I1 to n, right? But you know, this is the one. Okay, but notation wise, you can say a little differently. So that's your total flux, electric flux, right? So this is your total electric flux. Okay, so it's like kind of like electric field, right? And then whatever projection that's parallel to the area's direction. So that's so-called electric flux. It's like how many, you know, how much of this electricity is going out, right, over this area. Okay, it's kind of like the, you know, it's a electric field times area. All right. Okay, so it's kind of like a, yeah, it's not, it's a new concept, right? So now we're gonna say Gauss theorem says the following. Okay, Gauss law says the following, that the total flux, right, so which is this one here, E perpendicular delta A, which is the total flux, right, over this surface, right? And this is the closed surface, right? This is a closed surface here, so everywhere, right, add together. These two are equal, but that's also equal to this total charge that's inside, you know, that's being enclosed, okay? So you have this Q that's being enclosed. Whatever amount of Q that's inside this closed surface is called enclosed, right? So E and C. So this is the total charge, right? Total charge within, right? Or enclosed, right? So enclosed by, right? Within the surface, right? And this is a closed surface, okay? So not just that, you had to divide by this epsilon 0, which is the permittivity. Remember that? Permittivity, right? Of free space, which is equal to 9 times 10 to the negative 12, okay? And unit is, you know, you can, you know, unit is equal to, unit is equal to, oh, you know, the unit, you know, let me double check that for you, is equal to c squared, right? And then divided by Newton times meter squared. Okay, so that's the permittivity. So Gauss law says that the total flux is equal to the total enclosed charge divided by this epsilon zero, which is pretty remarkable, right? To come up with the law like that. All right, that's all we have. Okay, until next time, bye-bye.